We are back with more time series. In this video, we cover the so-called ARP models, which of course are a generalization of the AR1 model. Actually, maybe we can take a second to just present again the AR1, which has this form. The value at time t, xt, is expressed as a linear function of the past value of the process, xt minus 1, plus a noise. So without too much surprise, we generalize this by regressing xt on more values that are in the past. So what we will now call the ARP model, AR for autoregressive, is a model which satisfies this. Xt will be some linear function of xt minus 1, xt minus 2, blah, 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 up to xt minus p. Then, of course, we also add the noise, what we called before a white noise. And this white noise is then a random variable with a mean of 0 and a certain positive variance, which we denote here sigma squared. So obviously, this is a more complex model than the AR1 because we're adding parameters. We're saying that, okay, it's possible that, yes, xt is influenced by xt minus 1, but that's not enough in the sense that xt minus 2 also has a direct influence on xt, and maybe xt minus 3 has an influence, and so on. So we're simply regressing xt, but going further away in the past of the process. Now here we have a little note. This is simply, we're going to use this in the future. So you can know that the covariance between xt and the noise at time t, this is not 0, this is sigma squared. Well, yes, because careful, xt is a function of zt. You see, zt is here. So the covariance between this, which is xt, and zt itself, well, you would look at the covariance between this and this. It's 0 because zt is in the future compared to xt minus 1. Same thing, the covariance between zt and xt minus 1, that's 0 because zt is in the future compared to xt minus 2. But then you come to the last term, and of course, the covariance between zt and itself is the variance of zt, which is sigma squared. Yeah, so careful with that. The covariance between xt and zt plus 1, this would be 0 because now zt plus 1 is in the future. So there's 0 covariance between all the terms, between all the zt plus 1 and all those things. Okay, this is something that pops up a few times. Now, as we said before, to do fitting, we require our model to be stationary. Now, here there's a simple rule that will tell us if the process is stationary. Unfortunately, we don't prove it, but we can take this rule as given. Weak stationarity in the case of an ARP model is achieved if and only if each root of the so-called characteristic equation, okay, and this is the equation, is greater than 1 in magnitude. Okay, greater than 1 in magnitude. Let's explain what this means. Now, just look at this equation. The alpha coefficients are popping up here. So you have alpha 1. Okay, this is the same alpha 1 as in the expression of the model. You have alpha 2 here, which is the same as here, blah, 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 up to alpha p. And this is an equation of one variable, this thing called z here. So but you have z here, you have z squared here, you would have z to the 3 here, and then the last one is z to the p. When you solve this equation, meaning you find all the z's that satisfy this equation, 1 minus blah, 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 equals 0. When you find all the solutions, which would mean finding the roots, okay, the roots of this equation, the solutions to equations equals 0. Yes, if those roots are greater than 1 in magnitude, then you have weak stationarity. Greater than 1 magnitude means basically if you call your roots whatever, let's call them r for roots, it just means that you need the absolute value to be bigger than 1, which means, you know, if r is minus 2, then of course its absolute value is bigger than 1, so then you would have stationarity. But there's an additional complexity it's possible that the roots are complex. And so we need to deal also with the possible case where the roots are complex. So now, don't panic with this. If you've forgotten your complex numbers, we're not going to do anything complicated with this. And there's going to be examples in the tutorial booklet where some of the roots are complex. But we simply mean this. If we call one of the roots, one of the solutions to this equation R, it could be complex. So it on the if we place as usual, this is the reals and this should be the complex numbers, you could have a solution R would be here, but then you need to check that the norm, okay, or the norm of your solution, your R here, is bigger than 1 in absolute value, where this would be you can always write a complex number R as the real part, let's call this A here, plus I, the imaginary unit, times a certain B. Okay, and B would be what is on the y-axis, right? And then the root of this. Let me have it in a different color. The root of this R, if you recall, is just the length. It's just the length of this segment. So that's easy. It's just the square root of a squared plus b squared here, where again a is the real part and b is the complex part. Well, I suppose the complex part is I times b. Yeah. Okay, and again, there will be practice about this in the tutorial booklet. Okay, now, small example here. Just apply this rule. Is the following AR2 process weakly stationary? Let's just convince ourselves this is an AR2. Well, yes, because the model is xt depends on xt minus 1, xt minus 2, and that's it. Okay, and then of course there's the noise here. So maybe take a second to do this yourself. Apply the rule here. Okay, maybe you pause the video and you do it. I will show the solution now. The equation we need to solve is as given here. 1 minus alpha 1z minus alpha 2z squared. In our case, alpha 1 is 0.3 and alpha 2 is 0.4. So now we're back to our high school mathematics. We need to solve this equation, and we can use our quadratic equation here to find the solutions. Okay, so the solutions, the z's that make this expression equal to 0 are given here. You have your usual formula. I don't think there's not too much to say about this. Minus 0.75, blah, blah, blah. Okay, you can solve this. And here, just as a comment, okay, we get the two roots we get are not complex. Okay, they are real numbers. But what I said before is that it could be that sometimes you get a complex number. You would get a complex number if, of course, what's inside this square root, if this was negative, then you would have a complex number. Okay, but in this case, it's not the case. The roots are minus 1 and 1.25. Now this one is negative, but as I said, what you care about is the magnitude, okay, of the number. So in our case, the magnitude would be 2 and 1.25. Both are larger than 1. Okay, strictly larger than 1. Careful about that. It needs to be greater than 1. So it really needs to be a strictly greater than, which is the case here. So yeah, if for some reason you have a root that is exactly 1, you cannot conclude you have stationarity. It needs to be strictly larger than 1. Okay, so here, yes, we have weak stationarity. Okay, now in the next few slides, we do a bit of work to find the mean and the variance and the covariances and sorry, autocovariances and autocorrelations of the ARP model, like we had done with the AR1 model. Like all those slides spent some time to find the mean, the variance, and all the autocorrelations. So for the mean, that's easy. And here we will be under the assumption of weak stationarity. So assuming that yes, all the roots here are bigger than 1, we're under weak stationarity. The mean is very easy because you see the mean of this would be the same as the mean of this, the same as the mean of this. So just take the expected value, and by mean I mean expected value. Take the expected value on this side, expected value on this side of the whole thing. What will you have? Well, you will have call this expected value mu. So you will have mu, expected value here. Okay, now this is getting very cluttered. You will have the expected value here to be alpha 0 plus, well, this is also the expected value of xt minus 1 is of course also mu, the same thing, because we are under weak stationarity. So alpha 1 mu plus alpha 2 mu plus blah, 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 plus the last one is alpha p mu, and then the mean of zt is of course 0, because it's a noise. So then you just isolate the mu in this equation. You can send all the mu's, all the terms with the mu on the other side, and you solve for mu. You will get this expression here, okay? What I called mu is this, the expected value of x. Well, xt, but that's the same as the expected value of xt minus 1, or of xt minus 2, of xt plus 1. They're all the same. Now that's easy enough, but next we need to find the covariances, well, any covariances, meaning the covariance between xt minus k, for example, and xt, and for any k. Now, perhaps, unfortunately, there's not going to be one nice, neat formula we can obtain. What we will obtain is, in fact, a system of equations. So, and here the trick is to express one covariance as a function of other covariances, and in the end, you obtain a system of equations that you can solve and find all the covariances then that you like, or all the autocorrelations. But that's just overall what we're doing in this slide. But let's explain, and then after that, we'll give an example. For any k, here assume bigger than 1, you can write your covariance. So covariance between xt minus k and xt, like that. Xt minus k, just leave it alone, but then write your xt as what it is as a function of the past xt. So this is just replacing xt by what it is overall as here, a function of the past values of the process. So this is what is here. And now that you have that, you can simplify this covariance by taking all the cross terms, meaning, of course, the covariance between this and this whole sum will be the covariance between this and the first, and this term, because the covariance between a random variable and a constant is 0. So first term will be covariance between this and this, which is this. Okay, for now we just write it. As what it is. You can place the alpha 1 outside. Then you go and you check the covariance between this and the second term here, which is going to be, well, it's hidden here, but it's alpha 2 covariance between xt minus k and xt minus 2. And then blah, blah, blah. You keep going. The last term will be covariance between this and this, which is here. And alpha p covariance between xt minus k and xt minus p. Of course, because the covariance between xt minus k and zt is 0, because zt is in the future compared to xt minus k. So xt minus k doesn't contain any zt. Zt is a white noise. It's not correlated with xt, or xt minus k. Okay, and then now the next step is simply to write, or to realize that, okay, in our slightly simpler notation, covariance between xt minus k and xt minus 1, that's what we call gamma k minus 1, the autocovariance at lag k minus 1. Well, yes, because what's the distance between t minus k and t minus 1? Well, it's, I think you see it straight away, but it's t minus 1 minus t minus k. Okay, so it's k minus 1. Yeah, so this term here is really just the autocovariance at lag k minus 1. The other ones are the same. Okay, the second term will be the autocovariance at lag k minus 2, blah, blah, blah. The last one is the autocovariance at lag k minus p. And so here, this is what I said. We have expressed the autocovariance at lag k. Well, yes, because we started with that. We started with the autocovariance at lag k. Yes, the covariance between xt minus k and xt. We have expressed it as a function of the autocovariance at other lags. Which other lags? Well, k minus 1, k minus 2, k minus up to k minus p. Now, of course, this is very general because p could be whatever. P could be p could even be 1. In which case, we were back to AR1 where we don't have this. We just stop at k minus 1 if p is 1. But this works for any p. So if p is 2, well, we just need to stop here. If p is 3, we stop here, and so on. That's for the covariances, autocovariances. For the autocorrelation, very simple. You know that in general, autocorrelation at like k is just the autocovariance at like k divided by the variance of the process, also denoted gamma 0. And so just take this equation and divide both this and this by gamma 0. So this will become rho k, and then this one will become rho k minus 1. This one will become rho k minus 2. I think you see the pattern, and so this equation is valid. That's very good. We found autocorrelation, autocovariance. We have not found the variance actually of the process because well, this thing here was valid for k being bigger than 1, but we can easily find the first, okay, the first autocovariance, the autocovariance at like 0, also known as the variance of the process. We find like that. Same idea. Okay, you also start with this, but now k is 0. So if k is 0, in fact, of course, I'm just finding the covariance between xt and itself. Everything is still valid. Okay, you will still have, well, you will still have this, but with a k of 0. Now, if k is 0, of course, you have gamma of minus 1, but you know, I think that gamma minus 1 is gamma 1. Yes, something we've seen before. This explains the gamma 1 here. And then, again, if k is 0, you have, well, you have gamma minus 0, sorry, gamma minus 2. This is just gamma 2, blah, blah, blah. But we have this little sigma squared we shouldn't forget because now, here, imagine we're in the case k is 0. So the last term won't be 0. By last term, I just mean the covariance between xt and zt, that is sigma squared, as I had already told you here. Okay, so in the case of the gamma 0, the variance of the process, don't forget your sigma squared here. Okay, so now we have this system of equations. But in reality, but again, this doesn't tell you, it's not a nice formula that you can just use straight away. You have a system of equations that then you need to solve if in any given context you want to find specifically, you know, row 1 and row 2 and row 3 and blah, blah, blah. You need to solve those well, in the case of the rows, the autocorrelation, you would solve those equations. That might sound a bit abstract, but let's do an example. You'll see it's not especially hard. I'll remove that stuff. Okay, this is what I just said. It is a system of linear equations known as the Yule Walker equations. Well, yes, let's give credit to the people who came up with this, Yule Walker. And yes, if you have a model like that, well, like the ARP, where you maybe you know what the parameters here are, or you fitted the model. If you know what the alphas are and the sigma square, then you can find you can solve those equations and find the any rho k and any gamma k. Let's do an example. In the case of the AR2 model, now I just give you a general model. I'm not giving you specific numerical values for alpha 0, alpha 1, alpha 2. Find rho 1, rho 2, rho 3 as a function of those alpha coefficients. As a comment, if the question is finding the autocorrelations, you actually don't need sigma squared. So note here, I haven't given you I'm not even mentioning sigma square. You actually don't need it to find the the autocovariances, you would need it. But anyway, for now, I mean, try to do this by yourself. Pause the video. And now we present the solution. And it's, I should have said, it's really an iterative process. If you need to find row 1, row 2, row 3, well, you start by finding row 1, and then you can use that to find row 2, and then you can use that to find row 3. Okay, and again, we illustrate this with this example. Row 1, how do you find it? Well, just look at your general formula over here for the rows. Row 1 would be alpha 1 row 0, if k is 1 here, plus alpha 2 k is 1, so row minus 1, and that's it, because we have AR2. So here we stop at the term k minus 2, which in those cases is minus 1. This explains what we have here: alpha 1 row 0 plus alpha 2 row minus 1. But now, of course, this one, row minus 1, is row 1. Okay, so now we have an equation with only one unknown, because again, assume those parameters, you know what they are. So then an equation of just one unknown, which is row 1 here, you can easily isolate row 1, I mean solve and find what row 1 is as a function of alpha 1 and alpha 2. Simple enough. Now you're ready to find row 2. Row 2, the same general formula can be used. By general formula, of course, I mean this thing. So row 2 will be alpha 1 row 1 plus alpha 2 row 0, and that's it, you're done. Because you have AR2 here. So you stop at row k minus p. Okay, so row 2 is alpha 1 row 1, alpha 2 row 0. And of course, you've done good work. You know that row 1 is this thing here. Okay, so easy. You find row 2 as a function of row 1 and row 0. Row 0, by the way, as I haven't said, but of course you should know, row 0 is always 1. Yeah, of course, because it's row 0 is the correlation between xt and xt, which is 1. And then one last. Hopefully you see the pattern now. If you want to find row 3, well, you can find it as a function of row 2 and row 1. Again, using your formula from before, alpha 1 row 2, alpha 2 row 1, and of course, row 2 you found it before, it's here, and row 1 as well. You found it before over here. Okay, and then that's it. That's what the question asked, and I think hopefully you see the mechanics here. It's really an iterative process. Those are equations you can solve. But by the way, here we in the question we asked for row 1, row 2, row 3. Row 4 is in general not 0 either, right? So I could have asked you for row 4. I could have asked you for row 5. Okay, you would have done exactly the same process here. You know, row 4 is going to be alpha 1 row 3, and then plus alpha 2 row 2. Okay, again, always using this this function here, this equation here, but you know, I think you see the idea now. We're not going to compute those because we don't have all day. Okay, now we get to this important idea. Let me just take a sip. The idea being, or an idea, it's a fact. In fact, for an ARP model, what we have called the partial autocorrelation function is 0 at all the lags that are strictly larger than p. Okay, so there, and you could call this a cutoff property. If you have a if you have a AR3, the partial autocorrelation at lag 1 won't be 0, at lag 2 won't be 0, at lag 3 won't be 0, at lag 4, boom, exactly 0. why that is, I think we can see that if we remember the definition of the partial autocorrelation. And maybe it's worth it to go back to the slides about the partial autocorrelation, which are here somewhere. You see, we explained that the partial autocorrelation is simply that if we estimate xt as a function of all the previous values up to lag k, or k values in the past, I should say, the partial autocorrelation k is nothing else than this coefficient here in our prediction of xt as a linear function of the previous values of the process. But now, in the specific case of the ARP model, this approximation is not an approximation. It's exactly that, right? The ARP model is a model under which you have exactly that xt is a linear function of the past plus a noise at the end. Yeah. But then this explains why past lag k, the partial autocorrelation are 0, because literally in this process, you have xt, which is literally a linear function of only the p pass values. So then if you have a lag that's bigger than p, you could write plus 0 times xt minus p minus 1, but that's a 0 here. There's nothing there. I don't know if that makes a little bit of sense, that because for ARP you have xt exactly a linear function of the previous observations, past lag p, okay, maybe I misspoke earlier, past lag p, there's nothing to see. There's nothing at all, right? All the next coefficients here, if you keep going, I'm going to just change this to be p just for a second. All the others, if you kept going, adding linear terms, they are 0 just because the model is exactly this. Okay, hopefully that makes a little bit of sense. I read this is something you really need to know. For an ARP, the partial autocorrelation will be 0 for all the lags that exceed p, that exceed the order of the autoregression. And that's important because in practice, you can leverage this fact to choose the order of your ARP model, to choose p. Because if you have a time series data and you say, okay, I'm going to try to fit the AR model to it, well, what p should you choose? Well, it's easy with any software, or first it's going to be R, to plot the sample partial autocorrelation. Okay, so if you have a time series data and you plot your estimated fees, okay, the phi hat k you could call, and then at lag 1 you see it's large, at lag 2 it's diminishing, but it's still large, lag 3 here, and then let's say just that you have your significance level here for the partial autocorrelation, right? And then imagine that suddenly at lag 4 it's not significant, it's tiny, and then at lag 5 it's still tiny, at lag 6 it's still maybe negative but tiny. You see, that's some indication that AR3 in this example might be reasonable for your data, because at lag 3 the partial autocorrelation is still significant, but at lag 4, poof, it seems to be 0, or it's not significant. Okay, so this, I hope I'm not making this more complicated than it is. A way to pick the order of the AR model is to pick the last lag at which your partial autocorrelations are significant. Okay, as simple as that. And then the next slide, I believe, re-explains this in a slightly different manner. So let's review this slide. Yeah, so a procedure to select the order P of an AR model is as follows. But frankly, this procedure really is quite equivalent to what I explained here with this little ugly chart. Pick the last lag at which the partial autocorrelation is significant. But still, we should review this slide. So fit several linear regression models by least squares, as you would have seen in your stats course, one by one. Okay, and those are the other model you fit. They're increasingly complex. The first one, and I say linear regression in quotation mark just because the form is a linear regression model, but it's not the typical one where regressing xt on itself, but at one period in the past. So the first one is just the well, you could say this is this is in fact a AR1. Okay, so you go just one period in the past. The second one, you go 2 periods in the past. The third one, you go 3 periods in the past, and then you keep going, and you fit and you obtain your estimates of those parameters as usual by the least square method in linear regression. Now, there's a theoretical result you can prove, which unfortunately we don't do here, but it's given here. If an ARP model is true for your data, if the ARP with a specific P is true, and you have a large sample size, okay, so n goes to infinity, then the least square estimate of alpha pp will converge to the real parameter alpha p. But also, the alpha kk will converge to 0 for any k that is larger than your p here. Now, simply put, this means, okay, imagine that the real process of the data is a AR tree. Okay, well then this means that in your first model, this parameter will be significant, but now because it's significant, you try the next model. You try this model, and this parameter here, alpha 22, will be significant. Then you try the next model. Okay, this one will be significant. Again, here I'm assume the real process, is AR3. Okay, assume AR3 is correct. So then you've tried this model, then you go to the next one. Okay, but then this one will not be significant. Okay, this will be insignificant. Okay, this is what this says. Once you exceed the p, or the order, those parameters that you estimate by least square, they will be 0, or they will be non-significant. And then you would stop. You would say, okay, well, this was significant, this one was not, so I'm going to choose this model, and that will be, I will then choose an AR3 in this example. Now, how do you judge significance? That's a third bullet point here, which is nice, or it's a simple result. If ARP model is true, then alpha kk as a variance of just 1 over n. So easy. Alpha kk as a variance of 1 over n. Maybe we should have said, well, it has a mean of 0 as well, at least asymptotically. So this makes it very easy to judge the significance of this parameter. And then yes, so this gives you the procedure to select the order of your AR model when you do fitting. But now, lastly, there's a comment here. We use kind of we use this new notations, alpha hat kk, but the sample partial autocorrelation, what we would call what it makes sense to call alpha hat k here, the partial autocorrelation estimated from our data, those are actually the least square estimates of those linear regression models. Okay, so the sample partial autocorrelation, which you might call phi hat k per lag k, this is the same thing as the least square estimate alpha hat kk. So in fact, this whole slide is really just saying the same thing as I explained there. To fit an AR model, to choose the P, pick the last one that has a that has a significant partial autocorrelation. I'll pick the last lag at which the partial autocorrelation is significant. Okay, I hope that made some sense. Maybe okay, we just have one more slide and then one example. One theoretical slide, I mean, and then we have don't celebrate yet. There's a few more slides with more concepts, but let's wrap up this slide of selecting the order of the model. Yeah, so to judge the significance of this alpha hat kk, which again, maybe I should write this explicitly, alpha hat kk, this is the estimate of your partial autocorrelation at lag k. To judge the significance, you just use the statistic. Because if alpha hat kk has a mean of 0 when k is bigger than p and a variance of 1 over n, well, you know that alpha hat kk times square root of n, then we'll have a variance of 1. And it's also normal. Okay, so asymptotically, it's also the case that this statistic is conveniently a normal 0, 1, which makes it very easy to judge the significance of the parameter. Yeah, okay, under H0, okay, under the assumption that the parameter is 0, the fitted alpha times square root of n is a normal 0, 1. Okay, so at the significance of 5%, you would reject H0 if the statistics is, of course, bigger than the critical region, 1.96. Okay, again, specifically for 5% significance. And again, we'll see an example in a second, hopefully making this slightly more concrete. Now, one last point here. And frankly, I'm not entirely sure that everybody would have seen this AIC criteria before. You might have in your stats course, but let's explain. This is a very, very, very general criteria. It doesn't apply only to time series. And again, you might have seen it before, but it's a criteria you can use to pick a model when you have several candidates available. And here, maybe I should say, in this whole process, we're trying to give you rules to pick the P, okay, to pick the order of your model. Should it be 1, 2, 3, 4, etc.? It might not be that clear which one should be picked. So if you have two models that are, it seems that you could go for one and you could go for the other. Maybe this criteria, the AIC, which again is very general, could be used as a tiebreaker. What is the AIC? Let's read this equation: -2 ln of L. What is big L here? Maybe I should have written it, but let's write it now. L is just your old friend, the likelihood. Okay, so big L is just nothing else than the good old likelihood of your data. Now, here, I should say, we unfortunately will not explain how to find the likelihood of a time series. Okay, you could do that. It's not especially hard, but it does take a bit of work because you need to make some assumption about what the noise is distributed as. Usually you make the assumption it's a normal noise. And then the problem is that, of course, your observations are not independent. So you need to do some work to find the likelihood under the specific dependence structure of your time series. So we're not doing this in this unit. The R package or the R fitting will give you the likelihood. So you could have to use it in tutorial problems, even if in the exam, but R will give it for you. Okay, R will give you this precious likelihood. But provided you have the likelihood of your data under your model, then you can use the AIC criteria, because the AIC is nothing else than, okay, -2 times log of the likelihood, but then there's this thing, +2 n parameters. What is n parameters? N parameters simply is the number of parameters in your model. The number of parameters in your model. What does this do? Is simply this. In general, in statistics, you want a good fit. Okay, so you would want the likelihood to be as big as possible. However, usually you have also this concept of parsimony. You don't want too many parameters in your model because it makes your model more and more complex as you add more and more parameters. So the AIC, in essence, is finding a balance between a good model, meaning one that has a good fit, a high likelihood, and a model that has few parameters, because a small AIC is preferred. A small AIC is preferred. A small AIC, because there's a minus here, a small AIC actually means you want the likelihood to be big, because as the likelihood gets big, this whole thing gets small, and then you are minimizing the AIC. But you are adding this, which is a penalty. Okay, this you can really view it as a penalty for adding parameters to your model. So if you have lots of parameters, you're gonna make the AIC bigger, so you're gonna make the AIC worse, because again, we prefer a small AIC. So you see, this is a way to have a trade-off between a good fit, okay, a big likelihood, or said otherwise, a small negative likelihood, and not too many parameters, because again, if you add more parameters, you're going to make this thing bigger, and you're going to make this criteria worse. Okay, I hope that makes a little bit of sense. And again, in reality, or at least for this unit, you will get from our package. Well, the R package, when you do the fitting, will give you the AIC directly. Or in the test, I could give you like a numerical value for the likelihood, and you need to compute the AIC using this simple formula. Now, I think it's clear, but let's just make sure it is. And parameters here, I'm referring here to the parameters in the model, to the, a AR2 would have 3 parameters. Yes, because you, 4 parameters, sorry. AR2 would have 4 parameters because you have alpha 0, you have alpha 1, you have alpha 2. Don't forget sigma squared, okay? So AR2 has 2 parameters. AR3, of course, has 5 parameters, so that's more parameters. So alpha 0, alpha 1, alpha 2, alpha 3, and sigma squared. So you see, if you want to increase the order, maybe you're going to get a better fit, a better likelihood, but because you're increasing the number of parameters, you might actually make your AIC worse. Now, let's review this fitting with an example. You have collected a time series of size n equals 2000, and you obtain the below sample partial autocorrelation. Okay, and so here we denoted them partial autocorrelation hat. Okay, but this, we could have called this phi hat k. Or in our procedure here, where we fitted by least squared different regression models, this would then also correspond to our alpha hat kk here. Okay, so I guess we have lots of notations that mean the same thing. But in any case, the numerical values are given here: 0.31, 0.06, 0.20, blah blah blah. Simple question for you: which of those partial autocorrelations are significant? And if you were to fit an ARP model to this data, what P would you choose? So simple enough question, maybe try to do it while I revisit my Mr. Happy mug. Okay, and then we can present the solution. But you are not skipping doing it, of course. Okay, the critical value for significance, you can obtain it like that. Well, yeah, you take the critical region of the standard normal, you divide it by the square of the sample size, and you obtain this value, which is then your critical region for the for the significance of the statistic. Now, look at this value, 0.044. This one looks significant. This one looks significant. Yes, this one looks significant. This one is not. But then careful, this one is again significant. And then those two are not. So then you have that, yes, the partial autocorrelation of like 1, 2, 3, and 5 are significant. And so here, maybe there's a little bit of ambiguity. So what I mean is this: if you follow strictly the rule to pick the last lag at which the partial autocorrelation is significant, well, then you would pick an AR5. You would pick an AR5 because indeed, at this lag 5, partial partial autocorrelation is still significant. However, here you could make a case that because the partial autocorrelation at lag 4 is not significant, and that at lag 5 is not very strongly significant. Okay, by very strongly, it's a bit maybe ambiguous what we mean, but this is not much bigger than the significance we have found here. So because of that, it could be reasonable that AR3 is reasonable as well, and maybe for parsimony reason, meaning having fewer parameters, you could prefer the AR3. Now here, fortunately, we haven't computed the AIC, but then we could have computed the AIC, and in the case that AR3 is actually better in terms of AIC, meaning as a smaller AIC here, you could perhaps decide to choose the AR3 rather than the AR5. Okay, hopefully that makes sense. Now I suppose we go to it's more or less one last concept. I mean, okay, there's a few more concepts, I suppose. Residuals, model checking, and forecasting. Okay, so let's review them. In linear regression, you have this concept of residuals. Now here, I suppose you could say you have an analogous concept of residuals for a time series model. So now we're assuming we have real data. We have observe a time series data of size n, so can denote x1, x2 up to xn. And those things, the alpha zeros, hat, alpha 1 hat, etc., are the estimates of our ARP model that, again, we don't cover estimation of a time series model in this unit. But imagine you've done that with R, which would be using least square or maximum likelihood. So assume you have those parameters. Then you can define what is called the fitted value at time t of your process. What is the fitted value? Well, it is what your model is estimating xt to be as a function of the past values of the process. And that's easy to do. The form of your model is, as presented in the first slide, xt depends on the, alpha 0, and then t minus 1, xt minus 2, up to xt minus p plus a noise. So from your model, how you would estimate the next observation based on the past one is simply to use the equation of your model and replace the parameters by their estimate. Okay, so as simple as that. Alpha 0, you don't know what it is, but if you've fitted your data to the model and you've obtained parameter estimates for alpha 0, alpha 1, blah, blah, you replace them in the equation, and that gives you your fitted value of the of the process at time t. Now you could say, okay, if I actually know what xt is, provided that t is small or equal to n, that's true. You know what the value of the model is, but those x hat t, the fitted values, you actually use them to find your residuals. Okay, and this is what you care about here. The residual also would be the difference between the actual values and what your model predicts that the value should be at time t. Okay, and this is really like in linear regression, where you would, in linear regression, often you regress something called y as a function of the x1, and I suppose you have beta 1 plus x1 plus beta 2 x2, etc. So that you would have your y hat, right? And so your residual in linear regression often is denoted RT would be yt minus y hat. Okay, the prediction of what this y would be. But anyway, for us, our residual is xt, the actual observation, minus its fitted value or its prediction according to the model. And by the way, this, I suppose, an alternative notation for RT, I denoted RT for residual, you could have said this is ZT hat, right? ZT hat, by Z, I mean the Z that is here, because this is what you're trying to estimate. And maybe this is something we need to say. The Z here, we never observe them. Okay, like the errors in a linear regression, you don't observe them. You just posit that your model is this this expression, but plus a noise. But this noise, you don't observe it, but you can estimate it as the residual. Yeah, so the estimate of the noise, which you could call, I suppose, Z hat, this, this would be the Z hat would be your residual, what is called the residual here, what is called R here. Okay, so something like that. Now, as a comment, you can easily find the variance, or an estimate of the variance of the white noise like this. Okay, an estimate of sigma squared would be as given here. It is simply the sum of all the residuals divided by n minus 1 minus p. Well, yes, because the residuals, they have they have a mean of 0, right? They have a mean of 0. So well, yes, because well, if your parameter estimates are unbiased, then the expected value of xt hat would be xt, and so yeah, expected value of this would be 0, and therefore the expected value of RT whoops, squared is the same thing as the variance of RT, and remember that the RT are our estimates of the Zs, and the Zs have a variance of sigma squared. Now, this is all very formal what I'm telling you, but this is it's some sort of explanation for why this formula makes sense. That a sensible estimate of sigma square, denoted sigma hat squared, would be to simply take the average of the squared residuals. Okay, the average of the squared residuals. And look, here, there's a -1 because I suppose it's proven somewhere that this is we need the -1, as you often do, to have unbiased estimator. But here I would say, I suppose it's not, this expression is probably not that important, but I give it to you still, so you know how to estimate the variance of the Zs. Okay, enough with that. Now the slide, I would say, is quite important. You need to know how to do some basic checking of your fitted model. And by the way, next week we will spend some time in R doing all that stuff, but actually doing it and trying to see for a given data set what models seem sensible for our data. So here, this is all quite theoretical. We explain the procedure to pick the order and then do some model checking. We will actually do it in R next week. And here the idea is sometimes slightly confusing, so let's make sure we explain it. And here this is where we really use the residuals. Okay, so we need our residuals for checking that our model is sensible, like in linear regression. In linear regression, usually once you've done your fitting, you check if the residuals look like a white noise, that they're not correlated with the fitted values, that their variance seems roughly constant, and things like that, right? You really use your residuals as a diagnostic that your model fitting or your model is reasonable. So same thing here. But the idea that I need to explain is this: you can view your residuals as their own time series. Well, yes, because the residuals, which again is an estimation of your noise in your model, it is something that you observe over time. So you could say well, R1, R2, blah blah blah, or sorry, the residual are defined only for t bigger than p+1. But this series of residuals, you can view it as its own time series. Okay, it's observations over time, so it's a time series. Now, if your model is good, the residuals should look like a white noise, right? So that's the key ideas. view the residuals as their own time series, and if your model is correct, the residuals should not have any trend in them. They really should be a noise. They don't have, they're not increasing over time, they're not decreasing, they're not, and especially they're not, there's no autocorrelation within, within the white noise. Okay, and this is the idea we use now. Compute the autocorrelations of the white noise. Sorry, well, of the residuals. And here, the notation here I'm using just for this slide, rho hat k would be the sample autocorrelation of the residuals. Again, view this R, well, this series of R's as its own time series, so you can compute its own autocorrelation function, and you want this to be behaved like a white noise, so you should not see anything significant in the autocorrelation of this series of residuals, which is what is said here. If those residuals are independent, hence our white noise, and n is large, we have the result, same as before actually. The sample autocorrelations, again, of the residuals, they are normally distributed, they have a mean of 0, and they have a convenient variance of 1 over n, which is then used to judge significance, using this as a test statistic. This would then be standard normal. Okay, if when you compute that for several lags, it's not larger than 1.96, then there's nothing to see. The autocorrelations of your residuals are not significant. Okay, so if none are larger than 1.96, it's an indication that your model is adequate. Now, it's not a proof that your model is great. It's not a proof that your model is the reality, but it means at least based on this criteria, there's no red flag. Now, you can do that as well with the partial autocorrelation of your residuals. So why not? It should also be the case if your residuals are a white noise. You shouldn't be saying anything. You shouldn't be seeing anything in the partial autocorrelation. So same thing. Compute the partial autocorrelation of your residuals and check that none are significant. And again, in R, this is extremely easy because when you plot your either your autocorrelation or your partial autocorrelation, in this case, the autocorrelation, they always give you this little line, which is exactly the confidence interval that is presented in the slide. Okay, so if you see that, they really seem to all be or almost all be between those bands, then you don't have any significance. Okay, and same thing for the partial autocorrelation. By the way, it's not written on the slides, but the test for significance of the partial autocorrelations is actually the same. Okay, it's actually the same, meaning the under H0 that the series is an IID process. The partial autocorrelations also have approximately a normal distribution with the mean of 0 and a variance of 1 over n. Okay, last idea, which is forecasting. It's an important idea. I think, as I said previously, we don't do too much in forecasting, but in general, it's quite important. If you have a model of a time series data, why not use it to predict the future? To say, okay, based on our model, the next observation that, of course, we haven't observed because it's in the future, what would it be according to our model? And this is what we do in this slide. So here, assume that the last observation we have is xn. Okay, so maybe I've observed the I don't know, the inflation on several quarters or something like that, and so x1 would be the inflation on the first quarter I observed, x2 on the second quarter, blah blah. Xn is the last quarter, so the last observation I have for inflation. Okay, this is just an example, and let's say I've fitted a ARP model to all those data. How do I predict the next one, the inflation in the next quarter? Well, very simple. Just use your model. Just use the form of your model. Your model tells you that the the value at the next time should be linearly linked to the values at previous times. Okay, so you fitted your model, so you have a value for alpha 0, you have a value for alpha 1, use those, and that's it. And then, of course, because this is an ARP, you will stop at n plus 1 minus p. Well, yes, because in the ARP, if you predict the value at n plus 1, you will go back 1 time, 2 times, up to minus p times, well, up to p times back in the past. Okay, and that should tell you, well, that should give you your prediction of the future value, which is, you could say this is the fitted value at time n plus 1, but it's just a bit different than the concept of fitted value that we had before, because this was a fitted value for observations that we actually have, okay? Because then we could compute the residuals by taking the actual value minus the fitted value. Now here, we're finding the prediction is really finding the fitted value, but for observations that are in the future. Hopefully that makes sense. Now this one is called the one step ahead forecast. Well, yes, if the last observation I have is xn, one step ahead, so one period in the future would be x hat n plus 1. But you can keep going. At least in principle, you can then find your prediction 2 steps ahead. So 2 steps ahead, 2 quarters from now, what will be the inflation? You can use the same equation. Just be careful now. If you're predicting what the value will be at time n plus 2, you use the same model. So you still have your alpha 0, your alpha 1. But now, careful that you actually don't have the observation xn plus 1, because xn plus 1 is in the future. The best you can do, because you don't have xn plus 1, is plug here your prediction of xn plus 1. So you're going to use the x hat n plus 1, well, the x hat n plus 1 that you have found over here. Then you keep going. 2 pairs in the past with respect to n plus 1 is, of course, xn. This one you have it. It's an actual observation. And blah, you keep going up to n plus 2 minus p. And then you can keep going. If you want the prediction at time n plus 3, same thing. You will need to plug your prediction at time n plus 1, your prediction at time n plus 2, n plus 1, and blah, blah, blah. You keep going. Now, just as a comment, the predictions get worse and worse as you go further in the future, because, of course, this one, we're already using in the model what is not an observed data point, but a prediction. So yeah, the predictions, further and further you go in the future, they get more and more unreliable. And there's a way, we don't present it here, but there's a way to find some confidence interval for your prediction. And you see, typically they're very, very wide, even not very far away in the future, because again, predicting the future is almost by definition of a difficult task. But if your model can already be slightly better than just predicting the model by or just predicting the value by its mean, right? If you didn't have any of those models, you could say, okay, my prediction of x at time n plus 1, you just use the mean of the model, just use the expected value of the model. So if you can already beat that, just use the expected value by a little bit, well, that's already something. And lastly, as a comment, as you get further and further in the future, or meaning you make predictions about further and further away in the future, what you could call the m step ahead forecast for m that is increasing, this will approach the expected value of the process. As you get further away in the future, because the process is stationary, your prediction will go back to the mean of the process, because on the long run, your process is stationary. So on the long run, your process will go back to its expected value. So your m step ahead forecast, if m becomes large, will go back to your mean of the process. And we can probably illustrate that with this last example for this set of slides. So let's review. And here Josephine makes a comeback. I think we haven't seen her in a while. So Josephine has been recording the time she spends on social media every day. She denotes XT, the number of social media minutes that she has spent on day T. She fitted the AR2 model to that time series and obtained the following parameter estimates. So she's done the fitting already, and she gives us the values. Alpha 0 is 180, alpha 1 is 0.25, alpha 2, 0.15. As a side quest, maybe you want to double check that those parameters make the time series stationary. I'm pretty sure it does, but this can be extra practice for you. Let's just assume that this is weekly stationary here. Now, if her number of social media minutes was 160 today, 120 yesterday, what is your prediction? What is your prediction of her social media time 2 days from now? 2 days from now. So if we use the same notation as in the previous slide, we're saying xn, that's the last observation. This would be 160, and then xn minus 1, this would be yesterday, so that's 120. And we're looking for the 2 days from now, so not tomorrow, but 2 days from now. So we will be looking at x hat n plus 2. What is this? Shouldn't be too hard. You need to apply the formulas here. Take a moment to do it. Okay, so to get to x hat n plus 2, we first need to find x hat n plus 1. So x hat n plus 1, we just follow the formula. We start with our alpha 0 and then alpha 1 of xn. Just here, alpha 0, then alpha 1 xn. I remember it's 160. Okay, and then we add 0.15 of 120, the time she spent yesterday. This gives us our estimate for how many social media minutes she will spend tomorrow, 238. But now we, of course, want the 2-step ahead forecast, x hat n plus 2. And same formula, we use again our alpha 0, 0.25, but now 1 step before n plus 2 is, of course, n plus 1, and our estimate of x n plus 1 is 238, which was found here. And two days ago, with respect to n plus 2, would be today, would be the 160 minutes over here. And that's it. That's our answer, 263. And now, just as a comment, what is the mean, the long-term mean of the process? What is expected value of xt? Do you know the answer? Well, go back to your formulas. Okay, we're looking for this, but we have a convenient formula for that. It's alpha 0 divided by 1 minus alpha 1 minus alpha 2. Okay, so alpha 0 for us, what is alpha 0? 180. 180 divided by 1 minus 0.25 minus 0.15, and I believe this should be 300. So I'm just pointing out the fact that the mean number of minutes per day she spends on social media is 300. And here, this is just to link back to what I said. Your prediction as you go further in the future will revert back to the mean. And here, the last 2 days, she spends much less than usual. So I don't know why, but for whatever reason, the last 2 days have been a bit unusual, or at least much smaller than her average. So then, the 1 step ahead forecast, well, you can note those the 1 step ahead forecast is still smaller than her long-term or usual usage, 300. But you see, 2 step ahead is going to be closer to the mean, and then if you keep going like that, you're going to get back eventually to your mean as a long-term forecast. Okay, I think that video is already long enough, so I should stop talking, and I wish you a very good day. Thanks for watching. Hopefully I see you in the next video. And as usual, if you have questions, never hesitate to send them my way. Okay, so I will see you soon.